So for this meeting, we're going to solve additional problems related to our second lesson for this chapter. That is the kinetics of plane motion. So let's have our third problem. So this is our third problem. This is the problem statement. The body that has a weight of 128.8 pounds shown in the figure consists of two solid cylinders between which is a weightless drum. So find the acceleration of the center of gravity, the friction force acting, and the direction of motion. State whether slipping or perfect rolling occurs. This is our figure. So the larger circle represents our body that comprises of two solid cylinders. Therefore, the diameter of these um, two solid cylinders is equal to 2 feet. And then this inner circle that has a radius of 1 foot. This is the uh, the representation of our weightless drum. So if it is weightless, therefore it does not possess a mass moment of inertia. Only the two solid cylinders. Now we have here a an applied force P, applied tangent to the circumference of our weightless drum. So if we applied a force, so we are expecting that these two solid cylinders will rotate in a counterclockwise direction. So we also assume that there exists a friction between these two solid cylinders and the horizontal surface, no? But we don't know yet whether the direction is going to the right or going to the left. So let's explore that one later on. Now, let's start with the given, no? In answering a problem, you should note the given so that um, it would be easier for you to access the values of the parameters in your problem. So the given are the weight of the two solid cylinders, that is 128.8 pounds. RC represents the radius of these two solid cylinders, that is equal to 2 feet. RD represents the radius of our weightless drum, 1 foot. Mu S is the coefficient of friction, static friction of our surface of contact, that is equal to 0.25. Mu K is our coefficient of kinetic friction. So we are going to use this one if our body is in motion. But if our body is in stationary, we use mu S. So the value of our mu K again is 0.2. And then we also have an applied force P that is equal to 50 pounds. So what is asked in this problem, we have, I think, four requirements. The first one is the frictional force. So this frictional force acts at the point of contact, no, between the two solid cylinders and the horizontal surface. And then we also have the acceleration of these two solid cylinders, so represented by this A bar. And then the third one is the direction of motion. So where does these two cylinders roll? So either it will roll towards the right or towards the left baka. And then finally, let us tell whether um, our two solid cylinders will slip, no, with respect to the horizontal surface, or it would roll perfectly, no, on the horizontal surface. So let's explore that one, on which one is true, no, either mo slip ba siya or mo perfectly roll. So diri our first solution is we are going to create an FBD for our rolling cylinder. no? And then we're going to solve for the frictional force. So this is our rolling cylinder. We have here the the placement of our two axes, x and y. Now the first force that affects our system is the weight of these two solid cylinders, and then next is the applied force P, which is applied tangent, no, or applied horizontally and tangent to our weightless drum. And then with this applied force, so we can say that with a lesser amount of friction, so this applied force is enough, no, probably enough. So at this moment we can only make an assumption, no. So makayon na ta nga basig enough ni ang applied force P, which is equal to 50 pounds, to rotate these two rolling cylinders, or these two solid cylinders, counterclockwise. So represented by this alpha. Now, if your final answer is negative, so the true sense of the rotation of this solid cylinder would be opposite, no? It will be clockwise. Okay. Next, with this direction, no, with the direction of the angular acceleration, we can say that the frictional force, of course, would oppose this one. So our applied force will rotate, no, or will tend to rotate this solid cylinder counterclockwise. So our frictional force would resist this movement, no. So therefore it opposes the direction of the applied force. So direction of the applied force in this system is towards the right, so therefore our frictional force is towards the left. And since our solid cylinder is resting or is moving on the horizontal surface, so therefore the horizontal surface would also exert the normal force upwards. And then with this, so since this is a combination of translation and rotation, so therefore we also have an acceleration, no, a linear acceleration towards the right, no, and this linear acceleration is due to the resultant force, which acts at the center of gravity of this solid cylinder, or this rolling cylinder. Now we are going to solve for the frictional force. So this frictional force, no, since it is moving, so we're going to use the formula for the kinetic, no, kinetic friction. Okay, we're going to use the kinetic friction. So the kinetic friction, that is Fk, is expressed by the product of the coefficient of kinetic friction times the normal force. So given man ang mu k, so our mu k is given, that is equal to 0.2. Now, nagkuwang lang ta og normal force. So how are we going to solve for the normal force? So we are going to take summation, no, of forces along y. So if we take summation of forces along y, the net resultant force along y is equal to 0, meaning there is no acceleration, there is no net force, because along the y-axis, no, there is no movement. So therefore, statically equilibrium ang ato ang system. So that is equal to 0, and then we take positive if that force is directed upwards. So the only force that is directed upwards is only the normal force. So we have normal force minus na si weight, that is equal to 0. So therefore the normal force is just equal to the weight of our two solid cylinders, and that is equal to 128.8 pounds. Okay, so next we're now ready to solve for the kinetic friction. So our kinetic friction Fk is equal to 0.2 times 128.8, no? And this is equal to, so I'm going to use my calculator. So 0.2 times 128.8. So the result is 25.76. So 25.76 pounds. So this is the magnitude of the kinetic friction that is being applied by this rolling cylinder as it moves, no, as it moves towards the right direction. So we now have the value of our kinetic friction, no, or our frictional force. And I think this is the answer for the first requirement. Okay, that is equal to 25.76. Next, we're going to solve for alpha, no? Now, in order to solve for alpha, we take summation of moment of this system. Now, we cannot uh, use the summation of moment with respect to the contact point because there exists a kinetic friction. So if there is a kinetic friction, most likely our system will slip, no, or will slide. So therefore, we're going to stick to our original kinetic equation, which is the summation of moment along the center of gravity of this rolling cylinder. So we take summation of moment at the center of gravity, that is equal to the centroidal mass moment of inertia of our rolling cylinder times its alpha. So we take positive if that force would cause a rotation counterclockwise, because that is also the direction of our alpha. Now, we need to pinpoint, no, those forces that will not cause any moment of our system with respect to the center of gravity. And that is the weight, no, which acts directly at the center of gravity, and also the normal force. So eliminated na silang duha. So the only forces that cause a moment with respect to the center of gravity is only the applied force P and the frictional force F, or that is Fk, because we already defined that one, or we already solved for its value, no, from the previous slide. So here the applied force P will create a counterclockwise moment, so therefore positive siya, no. So we have P times its moment arm is equal to the radius of the weightless drum, so that is equal to 1 foot, minus the frictional force, that is K, no? Just put here K because we already solved for this one. And then its moment arm is equal to the radius of the solid cylinder, that is equal to 2 feet. That is equal to the centroidal mass moment of inertia of our solid cylinder. And the centroidal mass moment of inertia of our solid cylinder, no, we'll know that for the centroidal mass moment of inertia, or let's just put it here, no, but I bar is equal to, since this is a solid cylinder, so the formula for its centroidal mass moment of inertia is 1/2, don't forget this one, W over G. Now this is the weight of the solid cylinder and the square of its radius, no, that is C square. Okay, so let's put it here, 1/2 WG RC square and then alpha. So therefore, if we're going to modify this equation, our alpha would be P times 1 minus Fk times 2. This is all over 1/2 W over G, and then this is RC square, no? So our P is 50 times 1 minus Fk, that is from the previous 25.76, no? Our Fk is 25.76, 25.76, and then times 2, all over 1 half. And then, okay, this is not 27, 25 na siya, sorry. This is 25. 25.76, and then 1 half times the weight of the solid cylinder is 128.8 divided by 32.2. Our RC is 2 feet, so 2 square. Okay, so what would be the value of our alpha? So we're going to use our calculator. So we have 50 minus 25.76 times 2, then 0.5 times 128.8 divided by 32.2, then 2 square. So we have negative 0.19. So we have negative 0.19. This is radian per second square. Okay. So what does it mean, class? Kaning negative sa pasabot ani. So, pasabot ani, although the rotation of our kanang rolling cylinder is counterclockwise. So if we have a negative angular acceleration, it means that um, the angular velocity of our rolling cylinder decreases as it rotates counterclockwise. So ni-decrease siya at a rate of 0.19 radian per second square. Okay, so the negative angular acceleration indicates that the uh, the speed of rotation of our solid cylinder is decreasing, because of the negative sign. Okay, so next we are going to solve for the linear acceleration of our solid cylinder. So to solve for the linear acceleration, we are going to take summation of forces along the x-axis, no? So summation of forces along the x-axis, so that is the resultant force along the x-axis, and that is equal to the weight over g times the linear acceleration. Again, we take positive if that is going to the right, no? So again, since we assume that there is a chance that these two solid cylinders will slide, no, as it rolls along this horizontal surface, so therefore we cannot use the relation for the linear acceleration, which is equal to the radius times the angular acceleration. So we cannot do that because we assume that there's a tendency that this rolling cylinder would slide along this horizontal surface as it moves, no, or as it translates and rotates on its center of rotation. So again, let's take to this, and then we're solve for the a bar. So the only forces that acts horizontally is the frictional force and the applied force P. No, so applied for P is positive because that is going to the right. So we have P minus the frictional force, and that is equal to weight over G times a bar. So our a bar is equal to P minus frictional force all over weight over G. So the value of RP is 50 pounds, and then we already solved for FK, that is 25.76. Then all over the weight of our rolling cylinder is 128.8 all over 32.2. So what would be the linear acceleration? So we're going to use our calculator. So we have 50 minus 25.76 divided by 128.8 128 all over 32.2. So our linear acceleration is 6.06. This is feet per second square. So this is the value of our linear acceleration. No? So therefore, with the direction of our linear acceleration, it is understood that the direction of motion, no? Direction of motion is uh, towards the right. No? These two solid cylinders will roll towards the uh, right, no? Towards the right direction. So ang nisukuhay lang nila is the angular acceleration wherein nag-negative siya. So it means that as it rolls forward, no? As it rolls forward due to this force P, ang iyahang rotation kay may decrease siya. So ang kani siya murag naglibog kami ang uban kay ngano mo movement siya kanang towards the right sir tapos ang iyang rotation kay counterclockwise. So nahitabo ani although ni-rotate siya pa counterclockwise, no? Rotate siya pa counterclockwise. However, since na may sliding nga may occur, so samtang nagpull ta ani, no? Mo-move ni siya and then the same time mo-rotate siya pa counterclockwise pero mahinay na iya rotation, no? So ingana ni siya. Kay if wala pay if there is or if this is a condition that is perfectly rolling ni siya, so ang mahitabo is that the rotation is clockwise, no? Not counterclockwise. But since it is not perfectly kanang kwan rolling, so we're going to verify that one later. So may tabo na ay sleeping nga may occur, so therefore mo-move gyapon siya, mo traverse gyapon siya towards the right although its rotation is counterclockwise or opposing, no? Nay mahitabo nga ingon ana kay modanas man ni. So if dili gani siya modanas, so therefore this P is not enough, no, to translate our solid cylinder towards the right. But since dangog man day ni atong contact point, so therefore with a 50-pound force acting towards the right, so it is enough to translate this solid cylinder at a rate of 6.06 feet per second square. So that is to the right. Okay. So next, let's determine if sleeping ba or perfect rolling. So for a perfect rolling, no, perfect rolling gali, this equation will apply, no? The linear acceleration of our rolling cylinder is equal to the radius and the given angular acceleration. And at the same time, the given static friction, no? Because the static friction is the frictional force responsible um, for preventing this rolling cylinder to slide along the horizontal surface. So if the given frictional force is equal to the ideal frictional force, so therefore it is perfect rolling. But if slipping will occur, so this A bar is not equal na ni R alpha, and then the given static friction is lesser na, no? Less than the ideal. Okay. Now for the given static friction, so Fs given, that is equal to the given static coefficient of static friction times the normal force, no? Again, for this system, the normal force is just equal to the weight. So that is mu s times the weight. So the given mu s is zero point 0.2. So we have 0.2 times the weight, that is 128.8. No? So the magnitude of our given static friction is zero point 0.2. I mean, that is 0.25 there, sorry. Because zero point 0.2 is for the kinetic. So for the static, that is 0.25. So that is 0.25 times 128.8. So our given static friction is 32.2. That is 32.2 pounds. If this value, no, 32.2 pounds is less than the ideal value of the static friction, then we can say that slipping occurs. If this is equal, so therefore perfect rolling siya. Okay? But if this is greater than, say may tabo. So stationary, no? Meaning the given applied force, no, cannot move our solid cylinders. Okay, so we're going to solve, no, solving for Fs ideal. So to solve for Fs ideal, we're going to take summation of moment, but not along the center of gravity because we assume that it is perfect rolling. So we're going to use summation of moment along the contact point right here. No? So summation of moment along the contact point, that is equal to the mass moment of inertia at the contact point times the alpha. Okay? So if we take summation moment at the contact point, the normal force and the frictional force um, will not cause moment, no? So therefore eliminated sila. So only the applied force P, no? Because si weight also cannot create a moment, no, with respect to the contact surface. So only the applied force P. So si applied force P, it would create a uh, a clockwise, no, a clockwise moment. So that is positive siya if uh, mag-cause siya og clockwise lang, no, clockwise nga moment. So for this, our P is clockwise man siya, no, with respect to the contact point, but you can also follow the direction of alpha, no. So basig maglibong lang, so sige, let's follow na lang. Anyways, ang makuha ra magyapon ani is negative alpha ra man gihapon, no. So let's follow na lang kay mamaya to naanda, no. Follow the direction of the assumed direction of our angular acceleration. So that is counterclockwise, so therefore counterclockwise. Okay. So our applied force P would cause a clockwise moment, so therefore negative siya. So negative P times its moment arm with respect to the contact point, that is equal to the difference of these two radii. So 2 minus 1 is 1. So 1 lang. And then IC is equal to the centroidal mass moment of inertia plus the weight of these two solid cylinders and the square of the distance. No? And this is alpha. So let's solve for alpha. Again, the r here is the distance from the center towards the contact point. That is equal to 2 feet. So alpha is negative p times 1. Our centroidal mass moment of inertia is 1/2. This is solid cylinder, so Wg. And then that is the r square plus Wg r square. Or this is 3 halves things almost, no? So let's substitute. The value of p is 50 times 1, and then the denominator mahimo na siyang 3 halves, and then the weight is 128.8 divided by 32.2, and then r here is 2, so 2 square. So what would be the resulting angular acceleration? So let's use our calculator. So 50 divided by 3 halves is 1.5. Then the weight is 128.8 divided by 32.2. And then 2 square is 4. So we have a negative alpha na siya, no? So same ra gyapon sa itong nakuha ganiha, which is negative. So sakto sila nga mo decrease siya. So negative 2.083. So negative 2.083. This is radian per second square. Now to solve for f, we take summation of forces along the x-axis, no? So summation of forces along x, that is equal to the resultant force along x, so that is Wg, and then a bar. Now for perfect rolling, no? For perfect rolling, a bar is equal to r alpha, no? Mao man na ang perfect rolling. So ang forces nga may act in the horizontal axis are the applied force and the frictional force. So the positive force among the two is the applied force, whereas the frictional force is negative because it acts opposite to the direction of motion. So we have P minus F is equal to Wg times R alpha. Okay. Again, we take the absolute value of our alpha this time because we already know the direction of our acceleration, which is towards the right, no, towards the right. So therefore we use the absolute value of our alpha. So to solve for f, so f is equal to p minus wg times r alpha. Okay, so plug in the values. This is 50 minus 128.8 over 32.2. The radius is this is 2 feet, so 2 times 2.083. So the resulting frictional force, no, or this is also the static force. So this is 50 minus 128.8 divided by 32.2 times 2 times 2.083. So the result would be 33.336. So we have 33.336 pounds. Okay? So this is our ideal, no? This is our ideal static friction. So since, no, since uh, F is given is less than F ideal, therefore slipping occurs, no? So naa siya slipping, meaning mislide ni, no? Mislide ang ato ang kanang kuan rolling cylinders. Okay, so that is how you are going to prove whether slipping or perfect rolling ang nahitabo sa ato ang system. Okay, naay pangutana so far? Do you have any questions with regards to the solution of our problem number 3? Okay, sige, go ahead. Okay, sige, sige, go ahead. Okay, ang nahitabo man gud ani niya Matthew is that um duha ni sila ka kanang solid cylinders, no? So ingani ni siya. Although gi-state nga kanang kuan two solid cylinders connected na sila, however iya na gi-sum up iyang weight, no? Gi-sum up na niya iyang weight. So na siya weight nga equal sa given, no? 128.8. Tapos ang kaning naa sa kaning inner nga circle, it represents the diameter of our drum. So ang drum naka-attach lang na siya dira, no? Pag nakaana lang ba? Nakaalang ang drum. So that na kay rope dira, then gitali mo na siya ang force P. Imo na siya gibunlot. So therefore the mass moment of inertia is only for these two solid cylinders, excluding ang ato ang weightless drum, because weightless man siya. So by the formula of our mass moment of inertia, that is a function of the mass or the weight. So therefore wala siya gi-account kay negligible man iyahang mass moment of inertia because it is weightless. So wala siya giingon nga gi gibutang ni siya, no? Wala siya nga gilubong sa atong duha ka solid cylinder, gi-attach lang siya. In reality it could be welded lang, no? Gi-welded lang ni ato ang drum. So again, di ni siya hollow cylinder but still is solid cylinder as stated in the problem. Okay. What else? Naipangutana ang uban? Okay, wa man siguro. Basta ang takeaway ni ani is that kung perfect rolling, so you can use this ko ano, this equation or this formula, and also the summation of moment along the contact point. So you can only use this one if perfect rolling imo assumption. But if slipping occurs or na sliding and hitabo, so therefore there is a slight difference between the ideal linear acceleration and the actual. So most likely either kusog ang linear acceleration with respect to the angular acceleration, or both of them has a direct relation of their values, no? So again, there's a difference between sleeping and perfect rolling nga condition for rolling bodies. Okay, so next, let's proceed to the final problem. This is the problem statement. So we're going to determine the frictional force acting on the disk and the acceleration of the block shown in the figure if it rolls without slipping. So the statement sa ato a problem nga rolls without slipping, so therefore we can use the formula wherein the linear acceleration is equal to the product of the radius and the angular acceleration. And we can also use the summation of moment along the contact point, no? Then the small fixed pulley is frictionless. So the small fixed pulley is this one. This is frictionless, so no weight, no? Has negligible weight, so it does not affect the system. Then the weight of the disc is 128.8 pounds and the radius of gyration is 2 feet. Okay. So again, only the the this it could be the extrusion siguro, no, or it could be a drum that is attached to our disc, no, because we have an inner circle whose radius is 2 feet, so it could be a representation of our drum which is attached to our disc that has a radius of 3 feet, no? It could be that case, no, nga ani siguro ang porma sa ato ang system. Then we also have a block here that weighs 64.4 pounds. Okay, so don't forget to indicate the given. So these are the weight of the disc. R2 represents the larger circle, no, whose radius is 3 feet, and then R1 represents it could be the drum, no, the radius of the drum, which is equal to 2 feet. And then we also have the weight of the block equal to 64.4. And lastly, we have the radius of gyration of the disc plus this drum. So no need to um, formulate an equation for its centroidal mass moment of inertia, because this is very simple. With the given radius of gyration, it is easier, because the centroidal mass moment of inertia of any object that has a given radius of gyration is just the product, no, of the weight and the square of the radius of gyration. So simple as that. However, if the radius of gyration is not given, so you need to examine the geometry of the given object, no, or the given rigid body. Okay, so the requirements, we have the frictional force. So this frictional force always act at the surface of contact of our rolling body or our rolling disc and the horizontal surface, no. And then the second one is the acceleration of the block AB. So I just represent this AB as the acceleration of the block, because we have lots of linear acceleration here. I mean, in this system we have two linear accelerations. So let's explore that one. Now, before formulating or before creating an FBD, so let's analyze the the motion of our system, no. Let's assume lang. So it might change as we go along with the solution. So let's assume that our block, no, has an enough weight to pull this rolling disc, so that this rolling disc would translate in the right uh, in the right direction, no, so towards the right. So if this block, if we assume this nga it moves downward, so it has a linear acceleration, and we label that one as a bar B, no. So of course may tension dito, and then napoy tension diri. So as this block pulls this rope, so this rope is attached in this part of our disc. So the angular acceleration of our rolling disc is clockwise, no. So it would rotate this one, and since it rolls without slipping, so there is an enough static friction to maintain the contact of this rolling disc as it moves forward, no, towards the right. So therefore, our disc would also accelerate linearly towards the right, no, and that is a bar. This is our disc, so a bar D, no. So we have two accelerations this time, so we need to use our or we need to use our knowledge, no, from the previous lesson, wherein um we try to point out a moving reference point, and then we resolve the acceleration of a particle with respect to another particle. So, di ba, mao man natong gibuhat sa previous nga lesson. So, it's more on kinematics, no? So, in this final problem for this lesson, we're going to use um, the two principles. That is, we apply both the kinematics and the kinetics to solve or to analyze the motion of this rigid body. So, duha na. Okay, so let's explore that one. So let's start with the FBD of the 64.4 pounds nga block. So naa sa right side. So this is our block, and then there's a rope, no? So obviously the weight of the block acts downward, and then the tension of the rope acts upward, no? and then we assume that our block will move downward, so therefore this is the direction of our motion and the direction of our acceleration. That is represented by a bar b. Okay, so with this, we're going to take summation of forces along the vertical. But before that, in order for us to use the summation of forces, no, that is for static equilibrium equation, so we need to define first the reverse effective force. So the reverse effective force is always opposite to the direction of motion, no? REF. So summation of forces in the vertical equal to 0. We take positive if the force acts downward because this is the direction of motion. So ang forces can act downward, we have the weight of the block minus the tension and minus the reverse effective force, and that is equal to 0. But the formula for the reverse effective force, again, this is equal to the weight of the block over g times the linear acceleration of the block, which is going downward. Therefore, we have the weight of the block that is equal to 128, not 28, but 64.4. So that is 64.4 minus tension minus 64.4 over 32.2, then a bar b, that is equal to 0. No? So if we simplify this, so 64.4 minus the tension minus 64.4 divided by 32.2, that is 2. No? So 2 a bar b, and that is equal to 0. So that would be our equation number 1, wherein we have two unknowns, the tension and the linear acceleration of our block. So equation number 1. Next, we formulate the FBD of the disk, and then we're going to solve muna the relation of the linear acceleration of the block as well as the linear acceleration of the disk with respect to the angular acceleration of the disk. So this is our disk, connected siya via this rope, no? Nga attached siya sa frictionless nga pulley. So ang forces nga may act niini, first is of course we need to specify also the location of our x and y axis. And then unang-una, the weight of our disk, it acts downward. And then we all know that this is our assumed, no, direction of our angular acceleration, that is clockwise. And then since our disk, no, rolls over or rolls on this horizontal surface, no, by this drum, so there's a normal force that acts upward. And then we also have the tension via this rope which is connected to the block, no, so mana siya. And then with the given direction of our angular acceleration, which is counterclockwise siya, no, counterclockwise siya. So nahitabo ani is that although mo follow ta, no, so sa previous nga problem we follow nga if our assumed direction of our angular acceleration is clockwise, so automatic that our direction of our frictional force is towards the right. However, since these statements are problem that rolls without slipping, no? So kung rolls without slipping gali, this is free rolling. So ang direction sa imong force ani is, or the direction of your frictional force is opposite to the direction of motion. So the direction of motion of our disk is towards the right, no? Regardless of asab na siya ni tuyok, no? So if that is towards the right, then automatic the direction of your frictional force is towards the left, opposite siya sa direction of motion. That is that only applies for rolling disk that does not slip no, as it rolls on the horizontal surface. So di siya mo slide, more na siya ma-apply pero nagay slipping nga occur na given nga mga kinetic friction, so therefore mabalin ning ato ang direction for our frictional force. So ang crucial ra ani sa pag-solve is the direction of the frictional force, kay kung mamali ni siya marong tanan. Okay, so next, of course, we have the direction of our linear acceleration for our disk, so a bar d, and then we also have the linear acceleration of our block, no, padung siya sa kanang right. Now, to solve for the linear acceleration of our block and our disk in terms of angular acceleration, so ato tong gamit tong ato ang knowledge sa previous nga lesson, no. So wherein we use the vector equation, no. So ang ato ang particle of interest is the acceleration of the block, no, which is at the topmost part of our kuan, topmost part of our rolling disk. So this is our particle B, and then this is our moving reference point, no, moving reference point. Okay, moving reference point, that is our point D, or the disk. It represents the center of gravity of the disk. So we want to know the acceleration of this particle B because the acceleration of this particle B is also equal to the acceleration of the block, no? So we use the vector equation, no? That is the acceleration of the particle B is equal to the vector sum of the acceleration of its reference point, so that is the acceleration of the disk, no? Acceleration of the disk plus, no? Plus the acceleration of the particle B with respect to particle D, no? And that is equal to the normal acceleration and the tangential acceleration. However, no, there's a catch here. We ignore the normal acceleration. Kaya nga naman, because if we consider the normal acceleration class, the acceleration vector B will not follow sa iyahang na set nga direction because its direction is horizontal siya towards the right. Now, if we consider the normal force, what happens? So, say for example, ato na siya i-graph the wherein the vector acceleration or the acceleration vector of D is towards the right, and then naapatay normal force, I mean normal acceleration paana, and then tangential say paana. So therefore the resultant acceleration vector of B is naka-inclined na siya with respect to horizontal, and di na mao ang ato ang gi-expect because we already know the direction of our acceleration of B, which is towards the right, no, and very horizontal gid siya, no. So therefore we ignore the normal acceleration for this case because we already know the direction of our acceleration. So the only thing that would affect, no, the relative acceleration of our particle B with respect to the center of gravity of D is only the tangential acceleration. Okay, so to solve for this one, so nang una, we need to know the acceleration of our D, no? Acceleration of our D. So A bar D. Now, our A bar D for perfectly rolling cylinder, that is equal to R, that is R1, no, R1 times alpha. Then our given R1 is equal to 2 feet. So, sir, nganong R1 man? Because this inner radius is the one that is in contact with the horizontal surface, not the larger circle, no? Only the smaller circle. So, use the radius of the smaller circle. Kasi man ani contact lang sa horizontal surface. So the value of R1 is 2, so therefore AD is 2 alpha. Okay, so next, plus nimo sa relative acceleration of B with respect to D. So imo buhaton, imo i-fix si particle D. So i-fix na nimo kato-ato ang sign nga paana. So this is our particle D, which is the center of gravity of our disk. And then i-draw nimo ang line between B and D. So nadri ang particle B. And then since ato man gi-ignore iyang normal acceleration, only tangential. So muna siya ang direction siya ang tangential acceleration because this is the direction of our alpha. So what is the distance between B and D? That is equal to 3 feet, no? Or R2. Okay? So this is our AT. So number 2, our AT is equal to R2 alpha, or that is equal to 3 alpha. So we already have the tangential vector, no? Tangential vector acceleration. So the resulting vector is this one. So i-add lang nato, no? First is ato i-graph si AD. So A bar D. And then from the head of AD, i-draw po nimo ang tangential. So tangential pangato gihapon. So this is 80. So therefore the resulting acceleration is equal to the acceleration of our B, or in mathematical expression, that is just the sum of the magnitude of the acceleration of D and the tangential acceleration, no? This is B with respect to D. Okay, so therefore we have A bar B is equal to the magnitude of AD, no, plus the magnitude of AT, or ato lang tantangon ng magnitude sign basta kay kibota nga this is the magnitude of the acceleration of the particle B. So that is equal to 2 alpha plus 3 alpha, and that is equal to 5 alpha. So therefore naa na tay relation, no, between the linear acceleration of our block, which is equal to 5 alpha, and then the linear acceleration of our disk, which is equal to 2 alpha. So magamit na nato siya. So therefore sa previous di ay nga kuan, sa previous nga slide, no, naman ta atoy 64.4 minus t minus 2 times a bar b is equal to 0. So therefore mahimo din na siya og 64.4 minus t, and then minus 2 times 5 alpha. So that would be minus 2 times 5 alpha, ma-10 na siya. So therefore our first equation ma-change na siya into 64.4 minus t, and then minus 10 alpha. That is equal to 0. Again, this is the modification of our first equation. Now, may mo siyang minus 10 alpha. Okay? So, diri sa kaninga slide, we use the kinematic equations, no? Not kinetic equation, kinematic equations. So next, we're going to take summation of moment at the contact point. So why at the contact point? Because it is stated in the problem that this disk rolls without slipping. So therefore, summation of moment at the contact point, that is equal to the mass moment of inertia at the contact point times alpha, no? So we take positive if that force would cause a moment in a clockwise direction. So ato sa i-eliminate ang mga forces nga wa nag-cause og moment at the contact point, that is the weight, the frictional force, and the normal force. So we only have the tension. Okay, tension lang. So si tension would cause a clockwise moment, so therefore mo take siya by positive. So T times ang distance, no, sa ato ang tensile force or the tension force T and the contact point, that is equal to 3 plus 2, no? The sum of the two radii, 3 plus 2, that is 5. So 5, and that is equal to the yes, the mass momentum inertia of our rolling disc at the contact point is equal to the sum of its centroidal axis. So using parallel axis theorem, so do not put C na lang kay tibog na ka. So I bar represents the centroidal mass momentum inertia plus the weight of the disc over G and the distance of the center of gravity of the disc towards the contact point, that is equal to the smaller radius, no? That is R1 squared times alpha. So we're going to simplify this. So we have 5t. This equal to, again, for rolling disc, it is also the same with the rolling cylinder. So that is ang iyahang mass momentum of inertia is equal to the product of weight and the radius of gyration, no? So weight over G, then K square plus W over G, and this is R1 square, that is alpha. So ato siya ipang substitute ang values. So the weight is 128.8 over 32.2 and K is 2 square. Then 128.8 divided by 32.2, and then the inner radius is 2 square. This is alpha. So simplifying, we're going to use our calculator. So 128.8 divided by 32.2. Then we have 2 squared is 4 plus 2 times 2 is 4. So the answer is 32. So we have 32 alpha. So this is our second equation. So we now have a second equation. So ato na siya i-take note, no? 5t equals 32 alpha. So next, napatay usa ka or last equation, no? And that is in terms of the tension, the alpha, and the frictional force, no? So we take summation of forces along x, no? Along x axis. So summation of forces along x, that is equal to the resultant force, that is weight over G, and then the linear acceleration of our disk, a bar D. We take positive if going to the right. So ang mga forces nga ni-act horizontally are only the frictional force and the tension. So si tension is positive because it acts to the right. So tension minus frictional force is equal to weight over G times a bar D. But we already kanang identify the relationship between the linear acceleration of the disk in terms of kanang alpha, that is equal to 2 alpha, no? So 2 alpha. So therefore T minus F is equal to 128.8 divided by 32.2, that is equal to 2 alpha. So simplifying further by our calculator, so mahimo ni siya og 2. So 8 na ni, no? This equal to 8 alpha. And this is our third equation. Now, ato to siya ipang-combine tong ato ang equation nga generate, no, so that we can solve for the frictional force as well as the value of the kanang linear accelerations. Okay, so let's proceed. We're going to solve for F and A bar P. So combine equations 1, 2, and 3. So for the first equation, that is 64.4 minus t minus 10 alpha equals 0. So we are going to arrange this one in terms of alpha, second and tension, then last ang frictional force. So for equation number 1, we can transpose this one on the other side and this one leaving the constant. So it would now become 10 alpha plus T plus 0 iyahang frictional force, that is equal to 64.4. Now for the second equation, we only have 5T equals 32 alpha. So we can transpose this on the other side. So mahimo na ni og 32 alpha minus 5T plus 0 gyapon niya ang frictional force, and that is equal to 0. No? And then the third one, we have T minus F, that is equal to 8 alpha. So transpose the 2 on the other side so that it will become 8 alpha minus T plus F, that is equal to 0. So we're going to plug in these three equations in our scientific calculator and solve for the values of alpha, T, and F. So go to mode, press 5 for equation, and then press 2 for three equations, three unknowns. So we have 10, 1, 0, and then 64.4. Second equation, we have 32 alpha. Then we have negative 5 for the tension. We have 0 for the frictional force. Then 0. Finally, we have 8 alpha, negative tension, negative 1 ang tension, then 1 ang force, then 0 ang constant. So, muna siya ang result. For the acceleration, for the angular acceleration, we have 3.93. No, ato lagi kuan, 3.93. So, we have alpha equals 3.93. This is rad per second square. The tension of the rope equal na pod. So 25.13. 25.13. This is pounds. And then the force, mo na siya itong ipangita. That is equal to negative 6.28. Negative 6.28 pounds. Okay. And then next is our acceleration for B. So to solve for solving for A bar B, no? So namatay relation, no? A bar B, that is equal to kanang 5 alpha, no? So that is 5 times our alpha is 3.93. So therefore 5 times 3.93. So ato ko na 5 times 3.93. So the result is 19.65. So 19.65, this is feet per second square. Okay? Muna siya ato ang mga final answers. So naay pangutana so far? How about the others? Hello? Naay pangutana ang uban? Okay, so again, we have here a negative frictional force. So therefore, our first assumption is wrong. Okay, negative man ang nigawa, so therefore, this is opposite, no? The frictional force di is although we stick to our kanang ato ang kanang gi-assume nga opposite gid siya because this is perfect kanang perfectly kanang kwan rolling, but during the calculation we arrive a force of negative 6.28. Ang answer sa libro gi-absolute na lang, that is 6.28, no? So mo na siya yung final answer. The negative sign here indicates that the direction of the frictional force is not to the left but rather towards the right, the ICEA. Okay? So wa na jay pangutana? Wala na? Okay. So if na pangutana, then that's it, no? For this meeting.